So in this activity, I want us to just go back and reflect on what we have aggregated for this second order linear differential equation. So we've seen this again from kind of this mathematics approach, this Laplace transform or transfer function approach, and a state space approach. And each time we get a solution that looks like this. And so we haven't really very precisely talked about stability, but I think that from the plots that we drew for the first order case, we can kind of understand what stability means versus unstable systems. So unstable means that it's got pieces of it that are blowing up, that the value is growing and growing, or whether that's growing off to positive or negative infinity. But the value of the magnitude is getting large, whereas stable are ones that stay limited. And so what we want to do is we want to look at the types of solutions that we can get with these two exponentials. And we want to look back through where these R1 and R2 come from, depending on whether we're looking at it from a transfer point of view or a state space point of view. So I'd like you to think through what it is, what values of R1 and R2 allow this solution to be stable. And I want you to be able to express that. Look back at our past activities in this particular class and look at the values of those R1 and R2 that make it stable and how to express that in terms of the transfer function and in terms of the state space equation. And then think about whether or not this is something specific for the second order case or whether this will generalize. So again, go back to these past activities, take a look about where R1 and R2 came from, and identify, kind of precisely state what it means for the solution Y to be stable in terms of R1 and R2, and then articulate how R1 and R2 appear in the transfer function and in the state space equation of the system. So go ahead and press pause and try to come up with a phrase that expresses the criteria for stability. So as you're taking a look at the solutions that we've seen, we saw R1 and R2 appear in various different ways. One of the ways, when we compose the transfer function, those values R1 and R2 end up being the roots of the denominator polynomial. So in the transfer function, we have a polynomial on top and a polynomial on the bottom, and we're talking about R1 and R2 as being the roots of this particular denominator polynomial. So it's the part that makes the denominator 0. And so what we observe is that that's where R1 and R2 come from. And for this to be stable, we need R1 and R2 to both be negative. So it means that these exponents are decaying away rather than growing. R1 and R2 appeared as the eigenvalues of the state matrix. So we had our state matrix. We had to take the determinant of A minus lambda I and find the values that make that determinant equal to 0. So those are the eigenvalues, and that is exactly what R1 and R2 were. And so that means that R1 and R2, essentially the eigenvalues of the state matrix, those must be negative for this solution to be stable. So at this point in time, we can kind of start to introduce some terminology, and we're going to call these values that characterize the dynamics and characterize the form of the solution, we're going to call those the poles of that system. Effectively, this poles really refers to the zeros of the roots of this denominator polynomial. So poles, that's how they're defined. And so in the first homework, you would have seen, first and second homework, you would see the roles that these poles play in terms of essentially plotting a surface that represents the imaginary transfer function values, the complex transfer function values. So that's where those names come from. But we really ought to be a little bit more precise, because what we learned when we characterized these R1 and R2 is that they were really the solution of a binomial formula. And if you recall, we don't just have real solutions, we can also have complex solutions. And so it's not enough to just say that they're negative. That is not quite good enough. So what we need to say is to be a little bit more clear. And what ends up being the case is that it's the real part of the roots of the denominator polynomial, or the real part of the eigenvalues of the state matrix, that this is what needs to be negative. And so we'll see this really comes down to the fact that if you have e to the minus a plus or minus ib, what you'll remember is that this part is what determines the amplification or attenuation, and this is a sinusoid term. And so this will become a little clearer in our later activities. We've already seen Euler's formula, and that's really where that comes from. That this is essentially this imaginary term that is representing oscillation. And so it's really the real part that dominates the amplification or attenuation. And there's nothing that we did that is specific to second order systems. And so this does generalize. And so these are going to be these results right here. You need to definitely make these make sense to you, or have us chat with you until they make sense, because this is the key to the entire course. There's going to be a lot of other pieces that kind of add on to this, but this is one of the most fundamental results that we're going to talk about in this course.